Hi everyone. In this video, I will be discussing or explaining to you the idea of proving trigonometric identities. But before we touch on how to prove various trigonometric identities, let me explain to you what trigonometric identity is. So, when we're talking about trigonometric identities, I think basic question that may come to our mind is that basically what is identity? So in a simpler way, the way I put it is this. Whenever we are talking about identity, you know, it's like human identity, our identity, or someone's identity. We always talk about someone's or, a person character or characteristics, um, like a personality or something like that, right? So identity is always talking about a certain purpose, a certain characteristic, a certain personality. So if it's like something that is always true, like always true over time. So, for example, like I'm a man or I'm a person or something like that. So, same is true with trigonometric identity. It will be talking about a certain relationship with, of course, trigonometry because of the name of the trigonometric identity, but also in connection to that, it's something that is characterizing trigonometry. For example, the most basic one is that sine squared theta plus cos squared theta equals 1. So then in terms of how it is written, it may seem like it's similar to equation, but actually it's not. So the difference is this. When we're talking about identity, for example, the sine squared x plus cos squared x equals 1. The difference between equation is that in equation you are trying to solve, right? We are solving equation. That will be the purpose. So then, in other words, whenever we solve an equation, the equation is only true for certain values. Okay. Well, for identity, the difference is that it's not only for certain values, but this is true for x, basically all values of x, as long as x is domain. For example, if it's x real number, then real number. If it's the x is between 0 until 360, 0 until 360. So it's true for any values, you name it, that becomes an identity. So then that's why it's kind of explaining it. It becomes like a characteristics of trigonometry. And then it's something that you can actually prove from whenever we discuss the unit circle idea, that you can create any right angle triangle over here, right? And then this coordinates, this point, we can say the cos theta sine theta, where the theta is coming from this small angle here. So then here it's the cos theta, while here the height is the sine theta. While we know it's a unit circle, the hypotenuse must be 1. So then by using Pythagoras theorem, you can have cos squared theta plus sine squared theta equals 1. Or basically just swap the order, sine squared theta plus cos squared theta equals 1. So that becomes the identity, or one basic identity of trigonometry. So in the context of proving trigonometric identities, basically what we will be doing is that we want to relate or connect various identities, various characteristics of trigonometry. So later you will see an example what I'm trying to say. So some tips before we go on with the examples is this. Whenever you deal with the trigonometric identities, you will see that there are some of them are simpler, there are some of them are more complex. So whenever you want to prove one identity to be the same as the other one, you always want to have with the more complex one in general. But then in some cases, you can't really have that. Sometimes you will get like simple, so then it will equal to a simple one. So then you need something to do like a certain trick for that. But in general, we want to go with the more complex one, and then we make it simpler. And then that's usually starting with the left-hand side, not always. In other words, also you can start with the right-hand side. Another general tips is this. which is, I think it's really, really important, not only in math, but also in our lives. So we always keep our eye on the goal, and then in every step that we are taking, we always make a comparison with the goal. Yeah, I'll show you what it means in the example later. So the last 2 points are also really important, is that what we are trying to do in math is always we make use of what we already learned, okay, what we have learned. So whatever the skill, whatever the concept, whatever the formulas, like quadratics, factorizing, they all will come in again. Okay, so let's see here in this case, whenever you see this example of proving the identity, you see that the left one might look a bit more complicated than the left one than the right one. However, in this case, you can actually start from both sides. From either side will be fine. But then for a general idea, that I will start with the left hand side. Okay, so the left hand side, this is the way we write it. So I'll just rewrite the question again. And then by keeping my eye on the goal, so I need to check what's the goal. The goal is about secant x and cosecant x. So I'll need to keep in mind that basically secant x is 1 over cos, while cosecant is 1 over sine, right? So then in other words, whenever I try to play along with this, I want to come to the conclusion of having cos and sine as the denominator. Now, the important part of this, the note is really important, is that whenever you prove an identity, what you want to have is that you want to come to the conclusion that this is true. So that's why you come from the left, you make it to the right, or you start from the right, you make it to the left. So you're not trying to solve it, okay? So I'll start with the left hand side again, tangent x plus cot x. So I want to have cos and sine. Then it's impossible if I just stick with this, right? So I have to go with the basic definition. Tangent x is sine over cos. So I have the sine and cos over there. Cotangent x is basically the reciprocal of it, right? So I'll have cos x over sine x. So now I have at least cos and sine in the denominator. But the other thing is that the goal that we need to achieve is that this becomes only 1. While for now, I still separate it by addition. So then for that, to combine them, so I need to combine them by making the denominators common. So I'll have sine squared x here, cosine squared x here. So as we know in the basic identity, the upper side will be 1. So the denominator will keep it separate, right? Cos x and sine x. But as the goal is secant and cosecant, so I need to separate it again, like this. Then as the definition for each one, so I'll have this secant x and cosecant x. So it's shown. Okay, so you can definitely start from the right hand side and then you do it backward. That's if you start from the right hand side. So I'll give you the second example. For this one, again, you can start with the left, you can start with the right. So in this case, I'll start with the right hand side. Why? Because the right hand side looks a bit more complicated with the square and brackets. So I'll rewrite it again. Here, squared. So then, of course, first thing first is that I expand tangent squared x plus 2 tangent x secant x plus secant squared x, right? And then see the goal. The goal is here, we need to have only one fraction, and there must be sine x. There is no cos, there's no tangent, there's no secant, it must be sine. So I'll try to do it this way. Now that's a note that you need to make also. It doesn't mean that because the expert ones, the teachers, can do it very fast, it doesn't mean that they're so good. But they also have experience, right? They got it through the experiences. So here, in the case of doing this, it's very important that we go trial practices, right? So now we come to here, and then this, if you see, the upper side, you can factorize it so then it becomes sine x plus 1. But the below side is still cos squared x, and then we don't need cos. What we need is sine, so I can change it by using still the basic one. So from here, I can rearrange a bit, so I got this, right? And then you see, I don't need the sorry, this is squared. I don't need the 1 minus, I don't need the squared. So what I can do is that I can do it this way. I can factorize it like this. So then I can cancel, then I achieve the goal that I'm aiming to. Okay, so these are two examples. I'll leave this to you for you to try. So for the rest of this, if you want to repeat, pause, and then here and there you check it again, go ahead. So please feel free to drop a comment or ask if you need to ask any questions related to proving identities. Hope this helps. Thank you.